Hello everyone, my name is Abhishek Gade and today we'll be discussing about NASA 9 piecewise polynomial functions, and this method is used to calculate specific heat. Now it's developed by NASA and it's for two temperature model. Now because we need to focus on specific heat still, but we don't know what is a two temperature model. So let me give you some brief about that. So a two temperature model, how it's different from a one temperature model. So let us say we are having hypersonic flows which are at really high speed. What happens is that the fluid does not remain at one position for so much long time that the local equilibrium is not attained. That means it will always be in a thermal non-equilibrium because it's so fast. I imagine a bullet train is passing and you want to speak something to someone. Imagine the window is open and someone is there, your friend maybe. So, uh, but the train is so fast that when you're speaking, your information has not been passed to that person. So that is what happens in a two temperature model is, so there are four energy modes which we remember from our school days. The translational energy mode, rotational energy modes, vibrational energy mode, and electronic energy mode for the species. Okay, we have four modes. So what happens is one set will remain in equilibrium at one temperature and other in another temperature. So translational and rotational energy mode of species will remain in equilibrium at one temperature, whereas the vibrational and electronic energy mode of species will remain in equilibrium at another temperature. So yeah, next. So, before beginning, the story is all about internal energy. It starts with internal energy, it stops at internal energy. The internal energy of a molecule, the internal energy of an atom. So keep this in the mind, behind in the internal, that it's all about internal energy. And let's begin. So, first, the definition, the basic definitions. What is the specific heat and what is temperature? The specific heat is the amount of heat energy, how much heat energy is required to raise the temperature of a substance per unit mass. So it's per unit mass. So let's say for 1 kg, how much heat energy is required to increase its temperature by 1 degree Celsius. That is what is defined as specific heat. Another is temperature. Temperature is the degree of hotness or coldness measured on a definite scale. So the scale can be Fahrenheit, Celsius, or Kelvin scale. Yeah, these are two basics, but uh, need to start with this and yeah, slowly move into the advanced part. So first of all, I'm presenting you with an older version, that is specific heat as a function of temperature. So what NASA proposed before, which today we are not using, but what it was before. So it's like a polynomial parameterization. So when you see this equation at the first glance, you see it is a curve fit equation. It is not based on any theory or something. And you see there are now why it's saying that it is 7, because there is an enthalpy also coming in the picture, the entropy also comes in the picture, and there is where you can see the other coefficients, because uh, here which I haven't mentioned it here, only Cp is given. What is Cp? Cp is specific heat at constant pressure. So enthalpy would be integral of this Cp dt, and entropy would be the integral uh, 1 upon T Cp dt. So yeah, that is another story. But right now we are focusing on specific. But just to inform you. And so, uh, how many coefficients are there here? T A0, A1, A2, A3, A4, 5 coefficients are there. Okay, and T0, T1, T2, T raised to 2, T raised to 3, T raised to 4. These are the temperatures. Okay, so temperature. So if I plug in the temperature value, I have the coefficients. So for different chemicals, different gases, I would get the CP, that is the specific heat at constant pressure, and R is the molar gas constant. So that is simple equation given by NASA. Now, as you can see, it is Cp by R. It is a dimensionless form, and so this constant would take that units based on what are the temperatures. Again, this is an empirical equation. It's not based on any theory. Yeah. Let's move on to the new version. So what difference you're experiencing, like what you're seeing right now here, the new version? It's yes, there are two terms more now. Which two? T raised to minus 2 and T raised to minus 1. So why these two terms were added? When these two terms were added, the coefficients, number of coefficients, the what coefficient? Okay, I not started with a raised to 0 here, but first it was you should have started, but okay, you can understand. So one, 2, 3, 4, 5, 6, 7. 7 coefficients are there now. Okay, that is just a way to denote it. Start with a raised to a0 or a1. So what the thing is, there are 7 coefficients. Now NASA 9 coefficient polynomial parameterization means enthalpy and entropy in one of those. So in one of those 9 coefficients will come in, which I guess in entropy. So after integrating these equations, again this is in dimensionless form. This is an empirical equation, and we added this 2, t raised to minus 2 and t raised to minus 1. Now the benefit of adding these in the equation was, like, now we have more accuracy in predict in this CP for a wider temperature range. More accuracy, more good for making designs, and all this is done by NASA. Means we can understand this is all for hypersonic flows for their projects. Okay, so where the temperatures are really high. Okay, so but yeah, so when I'm saying about energy, there are four energy levels, molecular energy levels, and this we have learned in a chemistry, physics, both of them. So what are the four energies? One is the translational energy, means the molecules or atoms are translating in a direction. So we say I have X, Y, and Z. How much the movement of molecules is there? That is the okay. So first is that. Second is the rotational energy. So how much it is rotating about its about the three axes. So maybe it's on one axis it won't rotate as much as along the other two axes generally. So that is the rotational energy. Then comes the vibrational energy. So how much it's vibrating at its position with how much frequency. Okay, and next one is the electronic energy. So when the electronic transitions takes place with an atom or what molecule, electron shifts from one place to other. Okay, the transition at that time where the energy is there. So the first three looks like they are kinetic energy. Okay, yeah, we can see the vibrational energy is mixture of kinetic and potential energy, and the electronic energy would be a potential energy. So these are the molecular energy levels, and this forms the base to understand further and get depth in go into depth about this topic. So let's move on to the translational rotational specific heat. So before going on to this, we had four energy modes right now: translational, rotational, vibrational, and electronic. So translation rotational modes of specific heat are assumed to be fully excited. Okay, and the other two are like together are considered as dependent on temperature, but these two are considered as fully excited, and so we'll try to get the values here, and after that we'll derive what would be the vibrational and electronic specific heat together. Okay, so let's first get the values of translational and rotational specific heat. So I have two things. Maybe I have an atom or a molecule. I'm an atom like a helium, hydrogen, or a molecule, a diatomic molecule, hydrogen, nitrogen. So when I say like this, um, what is my Cp? That would be equal to Cv plus R. Now this is from the set of ideal gas equations, we know this. But then what is Cv for both the cases? Say for atoms and say for molecules. Now for atoms, like most probably, like they will be traveling in translational directions, like there would be no rotations. So remember the energy of a molecule. So how it was atom or molecule, how it was defined, it was defined as half kbt, and then if I add an avogadro number also, then it's half n kbt. So kV was the Boltzmann constant. Yeah. So but three directions. So half n kbt multiplied by 3. So 3 by 2 n kbt. Na kbt. So Na kb, this Boltzmann constant into Avogadro number, it's nothing but R. And so it would be 3 by 2 RT. Now this is the internal energy. 3 by 2 RT is an internal energy. But how to get the CV then? So CV is nothing but the change in internal energy with respect to temperature at constant volume. So del U by del T at constant volume. So what I had? 3 by 2 RT. Now I differentiate it with respect to temperature, I will get 3 by 2 R, and that is what you are getting here. So 3 by 2 R plus R, that would be equal to 5 by 2R, and that is the Cp translational rotational, the specific heat at constant pressure for atom or electrons. Similarly for molecule. So let's start. Um, Energy is given by half kBit. Then if I multiply the Avogadro number, half n kBit. Okay, Na kBit. Okay. So now uh, mm, rotational. So rotational, like I think for a diatomic molecule, it will rotate along the two axes, but on the third axis, the rotation will be negligible. So half into 2, half kbt, half na kbt into 2. So what it will be? It will be na kbt, and you can simply say it is RT. Okay. Now one we got one, but again there are translation is also there in three directions. So 3 by 2 is there already. So 3 by 2 plus 1, that is 5 by 2 n kbt, the total energy, or you can say 5 by 2 RT, the total internal energy of that molecule. Differentiate it with respect to temperature at a constant volume, and you will get the T will get being the T will be removed, and you will get CV as 5 by 2 R. And now if I add one more R in this, the CP translational rotational will be 7 by 2 R. So we have two values, 5 by 2 R and 7 by 2 R for atoms or molecules. So one thing is clear here. Okay, this is a constant. So the previous equation, the NASA equation which we derived, that was valid for thermodynamic equilibrium only. That is, when T trans rotational is equal to T vibrational electronic. But we discussed was that The translational and rotational modes are assumed to be fully excited, and so they are assumed it as a constant, and right now we derive that constant value. Okay, so it was 5 by 2r and 7 by 2r, right? So r is for species, okay? I haven't denoted a subscript, but rs you can say. So that is a constant. Constant means it is not going to change with temperature. It's independent of temperature, unlike the other two. Okay, so now we have the translational rotational specific heat. Now how to derive the vibrational electronic specific heat? So let's move on to calculate vibrational electronic specific heat. So I want to calculate Cp vibrational electronic, but if I say I know the Cp of at a temperature, so what it would be? It would be the summation of the translational rotational mode and the vibrational electronic mode as seen in the first equation on the page. So there are three terms here. One is the total Cp, the specific heat at a temperature, okay, is equal to the sum of the Cp translational rotational plus Cp vibrational electronic mode. So, from these three terms, we know two terms. Which two terms? First one is clear. We know the Cp translational rotational. We already derived it right now as a 5 by 2r and 7 by 2r, right? It is a constant, this term. Now, what is a variable? So, this Cpt vibrational electronic, how will we get this? This is from the polynomial equation, the empirical equation of NASA. So what will substitute this T vibrational electronic there, and we'll get the Cp from that polynomial equation. So what is the unknown? The remaining, it's the last term, and it is Cp vibrational electronic, the one which we want, and this is how just subtracting this Cp translational rotational from the total specific heat, we will get the Cp vibrational electronic. So this is all about the different energy modes. Summing up the entire chapter here, so the entire lesson, what we understand is there are four modes. There is a two energy equation. The four modes are translational, rotational, vibrational, electronic. Two energy equation means two modes are going to be in equilibrium at one temperature, and another two modes would be in another temperature. Then specific heat as a constant is not a constant here. It is a function of temperature, a function of temperature with different coefficients which will change for different chemicals and gases. And there was an old version, there is a new version from NASA, and slowly we moved on to how to calculate this specific heat for different modes, the set of modes. So first took we calculated the Cp of translational rotational from our basic energy equation of a molecule and the gas equation and all. So we got those values, and at last we finally calculated Cp, the specific heat at constant pressure for vibrational electronic mode, and this is how everything completed. So stay tuned for more upcoming lectures based on all these different topics in different domains, say multi-phase and heat transfer. Okay, so solid vibration, everything. And thank you for uh, all the love shown for the past lectures from my side. And I'm really happy on the comments and all the appreciation I'm getting from there. Stay connected with me on LinkedIn, and thank you.